Eins, zwei. 1, 2, 3. One, two. Okay, very good. Everyone's around. Very good. Well, we are back after a 2 years break, and I welcome all of you here in Utrecht. As you know, we were planning to do this conference 2 years ago. And then something happened. I don't know if you noticed, but it got cancelled in the very last minute. It was a tough time, at least to many of us or some of us. And so it's really exciting that we can now do it in person, this conference. That was also our goal. So we didn't want to move it online, because I think a conference lives from being together and talking to each other, seeing each other in person. And therefore, this conference is fully in person. But we will record the talks, and they will be available online afterwards. And then you can watch them yourself, or outside people can watch them. So, having said that, the issue has not quite disappeared. So the coronavirus is still around us. Well, hopefully not in this room. And therefore, we were thinking about what to do with the corona measures. Yeah. So how should we treat that? And it's a very difficult question, as you can imagine, because as I mentioned in my email, in the Netherlands, there are essentially no restrictions anymore, like in many other places, and people are very, easygoing. Yeah, so you can go into big venues and you can have big crowds without masks or anything. Now, we are an international conference, and things can be a little bit tricky if people come from all over the world. And I was told different sorts of stories, namely that if you have a conference where people wear mostly masks, then at the end of the day, most people are not infected. And if everyone is without a mask, it can easily happen that a kind of a cluster of infection arises. And therefore, we want to encourage you to be careful. Wear a mask if you're close to people. We have enough masks here. I know it's a little bit unusual because you go outside and no one is caring anymore, but especially if you're, say, close to a person on a poster board or something like this, where you very much close by, please be cautious and make sure that we are all safe. And I hope that will help to make this into an easygoing and safe conference. A few other announcements before we start with Sakura's talk, who's already up there for about half an hour. Let me mention that we have a lunch break, lunch is not provided here, but rather you are encouraged to go out, explore Utrecht a little bit. We are rather central, and you will find many places to have lunch in. Now, the Dutch way of having lunch is to eat a sandwich most of the time. So it's not that you go to every restaurant and you find a big lunch meal. So you have to be a little bit selective. It's available, but you have to check a little bit. And in order to help you, we provided you a list of restaurants on the web page. Okay. So a detailed list of lunch restaurants and dinner restaurants as well. Finally, we have in the afternoon we have the gong show, which is always a highlight of each conference. So with short talks, and these talks also they will announce some posters which are put out here in downstairs and upstairs. We also have poster boards, so you can walk around and check out the posters, discuss with the individual people, and this will happen after the gong show, where there's also a small reception with some food for everyone. Now, before we get to the talk, let me mention that we are here in a very nice venue. It's a Gasthaus, like a restaurant. It was originally a restaurant. It's not anymore. As far as I understand, it's now a recording studio for classical music. And you can also see kind of why it looks like this. And it's very well equipped with a lot of light shining down and cameras and excellent music equipment. So we are very happy to be here in this non-university location and be hosted here. So if you have any questions concerning the location, please ask the manager and or approach us. If you cannot find something, the bathrooms are, I think, in the back over there, and the password for the Wi-Fi is on the flip chart. Okay? So any questions, please come to me. Good, not to go too much over time. Let me say welcome again. It's very nice to see all of you. Thanks for coming here to Utrecht. And our first speaker today to open the conference is Sakura Schäfer-Nameki. And please, Sakura. And
okay, thanks very much, Thomas. Can you hear me in the back? Okay, fantastic. So, as the first speakers, I think we are all sort of seconding your thoughts on being back in person. Seeing everybody here is fantastic. I think the last time we met was in Oxford, so it's great that we are finally all in one place again in this sort of community between geometry and strings. I'll start off the conference with a talk on generalized symmetries, in particular string compactifications. And, okay, 1 second. So there's a pen. All right. So apparently I have to, oh, so now it doesn't actually change page anymore. Ah, it does. Okay, so, very good. We all are familiar with geometric engineering. We construct quantum field theories and some dimension D by compactifying on singular, most of the time non-compact, special holonomy space. And usually when you do this, you focus on the spectrum of local operators, the properties of local operators, and their symmetries, gauge and flavor symmetries, and so on. And what I'd like to do actually in this talk is to extend that to include charged things that are charged in a generalized symmetry, so these extended operators. So the main focus will be in a particular kind of geometric engineering, which is 5D SCFTs and Calabi-Yau threefold singularities, but a lot of that can be extended to other things. So you could apply it also to G2 and to F theory, to type 2B, whatever you would like to do. But I'll focus on this because it's extremely concrete and I've seen a lot of progress. And a lot of this progress in, okay, let me change color so you can maybe see this better. A lot of progress in 5D actually happened so just at the end of 2019 going into 2020, and so that a lot of that happened. So as I think Oren Bergman termed the second wave of 5D SCFTs. And so some of that I'll have to review, and in fact we can sort of reflect what actually would have been the type of topics that would have been covered in 2020 and 2021 at Geometry and Strings. And I think one of the topics would have been also 5D SCFTs. And there's been a lot of progress coming from 60, studying the flavor symmetries, looking at their Higgs branches, using brain webs or geometry. And we've seen some of that in Oxford already in 2019, but there's been a lot more. And we'll hear later in the week about that too. Another topic, however, I think that also would have showed up in 2020 and 2021, that has sort of really come into full swing in the last couple of years, is generalized symmetries in the context of geometric engineering. And of course, generalized symmetries in quantum field theory go back at least to 2014, but probably also much earlier. In terms of geometry, string compactifications, I think we sort of looking at 2020 and following years. So there's a lot to catch up, and I think we'll hear several talks and also poster. So talks by Jonathan Heckman and Federico Bonetti, and a poster by my student Dowie Gold. So we'll see a lot of that during the week, I think. So that's basically largely things that will be covered that are called higher form or higher group symmetries. And I'll explain what they are, how they're realized in string theory. But there's sort of an extra little piece of sort of generalization that happened really at the end of 2021, 22, and that's these non-invertible or higher categorical symmetries, in particular in dimensions bigger than 3. And there, I think we're still at a level of quantum field theory constructions, and there's not yet sort of an understanding how to realize them in string theory. So that's probably for the future. But I'll discuss one example just to give you a flavor of what kind of symmetries actually can occur in this sort of context. Okay, so in this talk, I'll discuss 3 things. One is give you an overview of what happened in sort of the realm of generalized symmetries, and then construct the higher form symmetries in geometric engineering, and then discuss the higher groups in the same kind of context. And please do ask questions, right? People can ask questions? Yes. Okay, so you could say people have gone a little bit wild on generalizing the concept of symmetries in the last couple of years. I think the main message you should take away is the modern sort of perspective on symmetries is a topological, oh, there's something here that showed up on your screen here. Okay, anyway, I put it away. Sort of like popping up messages, reading your emails. Anyway, so the main point I would like you to take away from this talk is if you have a quantum field theory, there are topological operators in it, you can most likely associate some sort of symmetry to it. It's not quite as simple as that, but that's sort of the guiding principle. You have topological operators, then you should be thinking of them as generating some symmetries. So one way of sort of thinking about the Noether kind of charges in Noether's theorem is really saying there's a codimension 1, say in 4 dimension, right? It's a codimension 1 topological operator that generates a zero form symmetry. So that'll be our terminology. That's just a flavor symmetry. So for example, if you have a current that's conserved, a continuous symmetry with a conserved current, and then you have a codimension 1 surface as d minus 1, then you can construct this Noether kind of topological operator that measures the charge. So the notation will be D is a topological defect. It's very important that these are topological objects. And always the subscript is the dimension of them. So they're codimension 1, so the D minus 1 dimensional. And lambda, the superscript, will always be some kind of group theory label. So here it could be, for example, just a label for the U1 charge. And this is topological because it doesn't matter when you deform this as D minus 1, right? You can squish it, shrink it, as long as you don't cross the charges. And these type of things will satisfy group law. I can multiply them and they'll just satisfy group law. So here, these lambdas will determine what kind of symmetry structure I'm generating. So these generalized symmetries generalize this sort of way of thinking about symmetry in various stages. So you start with higher form symmetries, where we relax that the objects are zero-dimensional, the charged objects, and the topological operators could be now some other dimensions. So in fact, if you have a p-dimensional defect, then codimension p plus 1 topological operators will generate the associated p-form symmetry. Then these types of symmetries don't necessarily need to form product groups. They could form some kind of non-trivial relations between, say, the flavor symmetry, the one-form symmetry, the two-form symmetry. So these are so-called higher groups. But all of these themselves are still sort of groups. They still satisfy group law. And then sort of going out even further, you could say, well, if I take two of these topological operators, like here, I could fuse them, and that could not be a group law, but it could be something like a fusion algebra. And if you sort of relax all of these kind of restrictions, you just say there's a bunch of topological operators, they generate some higher category, and I can try to study that. So what I'll discuss in this talk is essentially how, give you a flavor in this first part of the talk, what these constructions are, and then I will realize the first two in string theory. Okay, are there any questions so far? I actually need my glasses. Sorry, I really, can I get, because I can't see very well on the, sorry, because it's very small, and it's sort of this, anyway, I can keep talking. It's just that the iPad is tiny, and I can hardly see what's on this iPad. It's standing far away. Okay. Huh? Oh, fantastic. Okay, I think that's another plus. Okay, so now I can see what's on the slides. I don't have to fly blind. Good, higher form symmetries. So I think we've all heard about higher form symmetries. So here we have a gamma p form symmetry. So p form symmetry is generated by topological operators by our notation. So they're codimension p plus 1, and they're labeled by some g. And usually you can think of g being in some discrete abelian group. At least in higher dimensions, they'll be all abelian, and we'll be interested in discrete symmetries. So the way to think about this is, here's this kind of topological operator, and that can now link in space-time with a defect operator, this LP, and I can collapse this, I can shrink it, and then, in fact, by collapsing it all the way, I can define this as some charge, QG of LP times LP. So if this were, say, a zero-form symmetry, this is not anything surprising to you. For any kind of p-form symmetry, there is a background field, just like for the zero-form symmetry. And this is a p plus 1 form living in the space-time cohomology with coefficients in gamma p. And if I want to gauge it, because these are discrete symmetries, it means I actually have to sum over all these background fields. Now, a symmetry like this, so here I drew this LP as some defect, but a defect can also end, like a line operator can end on a local operator. So in fact, these kind of symmetries could become trivialized by what's called screening. So if you have a p-form symmetry, it can get screened by p minus 1 dimensional operators. So this LP, this p-dimensional thing, could end on an OP minus 1, and then I can take this topological guy and do the computation as before. So I collapse it, calculate the charge, but I can also just take it and strip it all the way off, and then there's sort of, right, because it ends, this LP, and then collapse it, so in fact, in this case, the charge becomes trivial. So this is what you would call screening. So so motivated by this here, you could then say, well, maybe we should think of these charged objects and some relations on them, right? Relations given by these kind of operators OP minus 1. So if I call LP the p-dimensional defects in the theory, I can define an equivalence relation on them, saying LP, the first and the second, LP1, LP2, are equivalent to each other if there is a p minus 1 dimensional object that's a junction between the two. And then I can ask, okay, if this is an equivalence relation, I can mod out the p-dimensional defects by this equivalence relation, and it will give me this quotient here. And in fact, this will be nothing other than the Pontryagin dual to the group. That's the p-form symmetry group. And usually this Pontryagin duality won't play a role because these are finite abelian groups, in which case this gamma hat is the same as gamma. So this just sort of, in certain instances, this might make a difference. Okay, so the simplest example is, of course, that's not zero-form symmetries, is p equals to 1. So we have line operators, and then the statement that two line operators are equivalent is just a statement. There is a junction, there's a local operator where these two lines can end. They can be joined together. So in particular, if one of them is the identity line, then actually it means there's a local operator and that other line operator can end, and in this way you can actually screen that particular one-form symmetry chart. So in a pure gauge theory, in any dimension, so pure Yang-Mills, where say G is simply connected, we have fundamental Wilson lines, and the only local operators will be in the adjoint. So in fact, this one-form symmetry, or it's Pontryagin dual, but they're the same, there's just a center of G. And again, there could be screening by matter. So this is sort of the picture of what is this higher form symmetry at work. Okay, so this is presumably something you've heard in many talks in the past 2 years. There's now this extension to higher groups. So higher groups is basically taking the screening picture and saying, well, this local operator that I introduced between two lines could actually also transform under something like a flavor symmetry. So let's actually say there's a flavor symmetry group, and we really need something like the actual group structure of the flavor symmetry here. So F0 is something like the simply connected group modulo some discrete group C. And then I can refine this equivalence relation on lines by coupling actually this whole thing also to backgrounds of the zero form symmetry, so flavor symmetry. And then I can define sort of pairs of lines, Wilson lines and the actual gauge theory lines and flavor Wilson lines. And then I can ask, so if there is now an equivalence relation between these two pairs, if there is a local operator that's now charged under the flavor symmetry in a particular way, right? So that these are flavor Wilson lines, and so in fact, these two lines, if you ignore this part here, this is just a picture we had before, but now I'm keeping track of the fact that this local operator could be charged under the flavor symmetry. And now I can again take these pairs of lines, the line operators and the flavor Wilson lines, modulo this equivalence relation. And that gives me another group E. And this E, this quotient, trivially, sort of by forgetting about the flavor Wilson lines, projects onto the one-form symmetry, or its Pontryagin dual. And also I can embed the flavor Wilson lines, so the C hat, by taking the it, R reps. And so, in fact, the C hat, which is the center of the flavor, so this was, remember, we had this flavor symmetry group, was a simply connected flavor symmetry modulo a discrete group C. This now comes into play here. And in fact, what we just constructed is these projections and these injections is just a statement that there's some exact sequence. I'm now removing all the hats because they're kind of not that important. So just think of it in terms of discrete abelian groups. So in fact, the one-form symmetry embeds into this group E, and then it projects onto C, which is the thing you quotiented from the flavor symmetry. And now if this actually is a non-trivial extension, right, then in fact what it means is that in cohomology, there's a non-trivial Boxstein homomorphism, where these are cohomologies with coefficients in C and gamma 1. And now you wonder, why is that actually important? Well, it's important because it says the variation of the background of the one-form symmetry is in fact determined by the background for the zero-form symmetry. So this sounds like it's an extremely Baroque kind of construction. The way you really should think about these two groups is in terms of these sort of equivalences on these line operators, the flavor Wilson lines, and there could be additional structure than just screening in terms of local operators. And the technical details are that the backgrounds for these symmetries are now actually correlated. So the one-form symmetry and the zero-form symmetry backgrounds are not independently choosable. Okay, so if you're a mathematician, you'll say a two-group symmetry is given by the data. There's a one-form symmetry, there's a flavor symmetry group, and some object that's called the Postnikov class, and that's just this thing we just constructed with this Boxstein. So it's some cohomology, the third cohomology class, in the classifying space of the flavor symmetry group with coefficients in the one-form symmetry. And from that, we can then construct the backgrounds delta B2 is the pullback of this Postnikov class. Okay, so we'll see an example at work where this all becomes a bit more transparent, but essentially you might think now, okay, this sounds like a very complicated construction, but actually the truth is these kind of two-group symmetries are really ubiquitous. So in fact, the simplest way to seeing it is if you gauge in a two-group symmetry, the one-form symmetry, right? So this is the two-group symmetry relation, the one-form symmetry, I can gauge this, then I actually get something that looks like a mixed anomaly. And actually more generally, I can look at mixed anomalies for the one-form and zero-form symmetries, and for example, gauge, say, one of these backgrounds here, and I can actually get also two-group symmetry. So there are various ways of seeing that, in fact, these symmetries that might look a bit unusual are present in very simple gauge theories. Okay, so far, right here, the zero and the one-form symmetry, they were still groups, but there was a relation between the backgrounds. So now we can also relax this last part, right? So far, all these topological operators, I fused them together, they just form groups. So there's some G and some H label, and the product gives us just the product, so the right-hand side of this fusion. But it's known already in 2 and 3 dimensions that topological lines, for example, don't have to satisfy this. They could satisfy a much more complicated fusion algebra. And that's actually what you could ask, whether that exists in higher dimensions. And until last year, I don't think there were any examples, and now there are a few examples, even in 4 dimensions of sort of these non-invertible symmetries. They're not called non-invertible because, you get a sum of these things. You can't just, it's not a group. So let me give you just a flavor. It's just a field theory construction. I won't discuss the string theory version of this, but it gives you sort of an idea of, how, again, ubiquitous such strange symmetries are. And this is literally a very simple kind of setup, which I think is illustrating this quite well. And this is something we constructed in this paper with Lakshya Bharadwaj, my student Leah Bottini, and condensed matter theorist Tiwari. So you take 4D, spin 4n gate Young-Mills, no supersymmetry, nothing. And, well, it's spin 4n. The center of this is the one-form symmetry. So that's a Z2 times Z2. And let's call them Z2S and Z2C. And then there's also Z2V, which is just a diagonal. So we said, associated to all these symmetries, there'll be some topological operators. For one-form symmetry, there'll be topological surface operators in 4 dimensions. So let's actually call the objects. So these are really, now I'm constructing some kind of category here. So there are now objects, which are these topological surface operators. There's the identity object. There's one associated to S, there's one associated to C, and one associated to V, and they will satisfy a nice group law. So in fact, the group law is written down here, where, for example, S times C will be V, and so on and so forth. So far, there's nothing non-invertible. It's literally just the spin 4n gauge theory. Now, in each of these topological surface operators, I can ask, there's also sort of the lines on each of these surface operators. But actually, to start with, there's just on each of them, there's some trivial line. Now, this system, this spin 4n theory, has also a Z2 outer automorphism. I can sort of, in this Dinkin diagram, I'm just exchanging those 2 legs. So it actually, there's a gamma 0, so the zero form symmetry. That's a Z2, and that will exchange exactly the S and the C, guys. And one thing I didn't, so these DIs, right, also, of course, the topological lines will satisfy a group law, right here. So for both the surfaces and the lines. And now if I actually quotient by this Z2 action, I get what's called the pin plus 4n gauge theory. And the statement is now this pin plus 4n gauge theory has non-invertible defects, topological defects. So I will give you sort of some things I'm putting under the carpet because you don't have time and I haven't talked about geometry yet and you all want to hear about geometry. So there's some things you can ask me about later. But basically the first thing is you take invariant combinations of topological surfaces and topological lines. And one thing we see immediately is that, well, there's now some linear combination of the topological surfaces for S and C, which actually will become something that's now a non-invertible kind of object. So the fusion of, for example, this object here, which is this linear combination, this invariant combination, will be something like the SC, so the square of it will actually be the identity and plus the V. So that's sort of a very simple way of seeing this. To get to this, it's not just expanding out this product. There's a little bit more to that. But as I said, you can ask me. But we also gauge now a zero-form symmetry. So when I gauge a zero-form symmetry in 4 dimensions, I get a two-form symmetry. So there's now a Z2, two-form symmetry, which has generators which are topological lines. So there's a topological line which is called D1 minus, say, and that generates this Z2 two-form. And now you could ask, in the set of lines that I had at the beginning, right, are there now additional lines on these topological surfaces that I need to take into account? And in fact, it's true that in fact there's the identity line, there's this new line, D1 minus, there's a line on this SC surface, but then on the V surface, the invariant, right, there was a topological surface that's D2V, which actually is invariant, and there's now a new line, a topological line, D1V minus. And this now actually will put all of these topological lines participate in this non-invertible fusion. I didn't explain to you how we get this, but this was to give you a flavor of how simple a system you can look at and get these non-invertible symmetries. So this is nothing that should be super exotic. It's literally something that happens by taking a pure gauge theory, Yang-Mills in 4 dimensions, and gauging a zero-form symmetry. Okay, now let's connect this to geometry. So what time did I start? You went a bit over, no? Okay, so then I have until 35 maybe. Okay, good. So let's connect this to geometry. So one question that I think, there are many interesting physical motivations studying these generalized symmetries, which I will not have time to discuss. Anomaly, Toft anomalies, the vacuum structure, confinement, and so on. But actually what I'd like to go into now is how do we generate or how do we implement these and detect these in string compactifications. And this will be in the geometric engineering framework of 5D equals 1 SCFTs. So let's just recap very briefly. I think this is sort of preaching to the prophet here. 5D superconformal field theories. We take the M theory, put it on a canonical threefold singularity, some non-compact Calabi-Yau. It can be isolated or not, and we compactify it to 5 dimensions. And I will assume for simplicity that we can resolve this completely. If you can't, then you should come to Andres' talk on Friday. He'll discuss sort of other types of singularities where you cannot do that. So I actually assume that all these things, when I resolve, are actually not there. So canonical singularity means superconformal field theory in 5 dimensions. I can resolve it, so Kähler parameters, that is the Coulomb branch of the 5D theory, and then the complex structure deformations which feed into the Higgs branch. And there's of course a lot more than the Higgs branch and just complex structure deformations, but we will not discuss that, we won't need it. Okay, so we assume we can resolve it, and then there's a nice dictionary, of course, how we get from the geometry to the data of the 5D theory. In M theory, you have the C3. We expand it along 1-1 forms that are dual, point-grade dual to the compact divisors. So let SA be the compact divisors, and then the rank is just determined in terms of how many compact divisors we have. And the gauge coupling is sort of inversely proportional to the volume. Flavor symmetries then naturally are related to non-compact divisors. So in fact, B2 of this X2 tilde, X tilde is actually the rank plus the flavor rank of the theory. And so by resolving the theory, using this sort of reduction from M theory, we get some U1 effective description with matter and Chern-Simons couplings. And the matter will come from additional wrapped M2 branes. And again, the important thing here is to sort of detect what kind of M2 brane states we have. We have the W bosons, which come from -2, 0 curves. We have -1, -1 curves, and which will correspond to matter hypermultiplets. And then sometimes we can go to specific points in the Coulomb branch when there's a non-abelian gauge theory enhancement. So this is when the surfaces actually have a joint ruling. And the CFT is just collapse all these surfaces back to 0 volume, and we go back to the canonical singularity. Okay, this is very standard, very sort of well-known things. Now we have a non-compact Calabi-Yau. So you could ask, even before you think about higher form symmetries, is there a role that the relative cycles, so non-compact cycles, will play? So this Calabi-Yau will have homologies, which are X is the Calabi-Yau with respect to its boundary del X. So these are non-compact Q-dimensional cycles, and we can wrap M2 branes or M5 branes, and they will give rise to massive excitations. So in fact, these are non-compact cycles, so in fact, there'll be infinitely massive excitations. An example is take H2 of X, del X. These are non-compact 2 cycles. They extend to the boundary, and we wrap an M2 brane on that, and that gives us now the world line of an infinitely massive particle. So we are in Euclidean signature, so this is actually a line operator. And so now we can really reconstruct the screening picture. So we had this gamma 1 hat was the lines modulo equivalence relation. Equivalence relation was 2 lines are equivalent if there's a local operator. So now we can formulate it in terms of this relative homology and the homology of this Calabi-Yau. So the M2 branes on compact cycles, right, so H2 of X, those are finite mass particles, these are local operators in 5D, and the non-compact 2 cycles, the relative 2 cycles, those will be the line operators, and this equivalence twiddle thing will be effectively this quotient. So the one-form symmetry, or the Pontryagin dual of this one-form symmetry is this quotient in relative homology. Now, these are 2 cycles that extend to infinity, so it's very natural to think they actually will end in 1 cycles on the boundary. So can we actually think of this also in terms of the 1 cycles? And indeed, just using this long Z sequence, right, they will actually embed into H1 of the boundary. So these are actually 1 cycles on the boundary. They become trivial as you move into the bulk. Okay, so that's sort of the first construction of higher form symmetries in this M-theory context. Now, computationally, if you actually have your Calabi-Yau resolved it, this is not the most practical way of actually going about calculating it. There's a simple way of seeing that, in fact, all you need is the intersection matrix of compact surfaces and compact curves, and then you just take this quotient of z to the b4 modulo this matrix of intersection numbers times z to b2. Another way of computing it is actually taking the perspective from this H1, from the boundary, and in fact, for many toric models, for example, we know exactly what the boundary is. So for example, the toric Sasaki-Einstein YPQ manifolds, or the cones over these are canonical singularities, and they give rise to SUP level Q 5D theories, and H1 of these YPQs is just Z of GCD P comma Q. And that's actually expected from this description because we have an SUP gauge theory. We have the level Q just tells us there's actually a particle, an instanton particle that's charged Q, and so we actually screen part of the one-form symmetry to exactly this GCD. The nice thing about this geometric perspective is also that we can apply it to theories that don't necessarily have a gauge theory description. There's no non-abelian description at any kind of point in the Coulomb branch. So there could be non-Lagrangian theories, like the Seiberg P2 theory, and that has a Z3 one-form symmetry. Now I put a subscript E here because this is really coming from the M2 branes, and naturally you could ask, well, I could have also wrapped M5 branes, and you could now construct sort of following the same logic, right, the screening argument here, and you can generate various types of higher form symmetries as labeled here from these types of relative homology quotients. And in fact, for example, for isolated hypersurfaces, you'll find there's a 3-form symmetry. Okay, what else I want to say? Right, so this is, in M theory, a way of constructing these higher form symmetries. Now, the 2-group symmetries are a little bit more fiddly, because for this, we really need to know what actually is the global form of the flavor symmetry group. So it's not just about flavor symmetry algebras, which you can find in the literature, but you actually need the flavor symmetry group. And so there are 2 ways of doing this construction that I'll discuss, and I think Jonathan will discuss something related later on. So one is to just compute this extension group E that I was talking about earlier from intersection numbers in the bulk, from X tilde. And then there's another, and this was done in this paper with Fabio Pruzzi, Lakshya Bardash, and Jiwano, exactly a year ago, actually. And then there's a second perspective, which looks more at the boundary, and It's sort of this philosophy of thinking most of these things should actually not depend on how you actually resolve, deform the bulk, but it should really be something, a property of the boundary of this theory, of this geometry. And that's work with Michele and Iñaki that we wrote earlier this year. And that will tell us about these two group symmetries in M theory. So let me just briefly go through this intersection calculation. I won't give a lot of details. You should go to Dawei Gold's poster, which I think is up there. So he will be able to explain to you more how to compute two group symmetries, also in 6 dimensions. But the point is, of course, we said before that the main difference between just computing one form symmetries and these two group symmetry is you also take into account additional transformations under the flavor symmetry. So in fact, the object that we would want to consider is not just these compactifications, intersections between compact cycles, compact 4 cycles and compact curves, but now also the non-compact, the flavor symmetry divisors with the curves. And that now gives sort of this quotient, which is now exactly calculating this extension group E. So one simple example where this occurs is the SU2 0. So that's again another point that these two groups appear sort of really in very, very simple theories too. So SU2 level 0 in 5 dimensions has this nice toric description, and taking the description where the flavor symmetry is manifest using the surface F2. So we have one compact divisor here, and then we have sort of the flavor guy sitting here. So this is going to be the thing that gives rise to the non-abelian SU2 flavor symmetry algebra. So in the Coulomb branch, we resolve this, and then we have curves which are E and F. So these are just the Hirzebruch E and F curves, and the intersections with these divisors, compact and non-compact, are just these here. And so now we can, so indeed the flavor symmetry, the simply connected version is SU2, but actually it turns out that is not the flavor symmetry group. The flavor symmetry group is in fact SO3. And so that's actually where all the meat of this matter sits. So the computational device of any kind of higher form symmetry calculation is the Smith normal form decomposition, SNF. Smith decomposition or something in Mathematica, you hit sort of this intersection matrix and you find 4,1. And now E was just a quotient with respect to this. So this is this quotient here. And so what we're finding here is that E is actually Z4. The one form symmetry of SU2 with no theta angle is Z2. It's just the center. So in fact, that embeds, it projects onto Z2. And so in fact, this is now this discrete symmetry that we have to quotient to get the flavor symmetry group. So in fact, we get an extension, and this extension, of course, does not split. And so we have a very good chance of seeing a 2 group. That the flavor symmetry group of SU20 is SO3 is also known from the superconformal index and some anomaly considerations from these papers. So that just confirms that. Okay, so now how does the 2 group emerge? Well, the flavor symmetry is SO3. There can be an obstruction lifting the SO3 bundles to SU2. That's generally called the second Stiefel-Whitney class. So W2 is an H2 of BSO3 with Z2 coefficients. And then delta B2, the background for the one form symmetry, has a variation which is given in terms of the Brockstein of W2. And that's a non-trivial W3 class. And that's our 2 group symmetry in these 5D theories. Okay, do I have time for this? Yeah, I think so. So that was, you can see now the key that goes in is intersection numbers. We can compute now these higher groups in any 5D theory that we'd like. Okay. Now there's another perspective, which is what we discussed in this paper with Michele and with Iñaki, which is, let's think of this, right? Even the one form symmetry was something we could detect from the boundary. So is the 2 group also somehow something that we can just observe by looking at the boundary of these spaces? One small caveat here is that we actually need the Calabi-Yau realization to manifestly have the non-abelian flavor symmetry. And I think this is sort of something that needs to be thought about more carefully, because clearly in this context here, from these intersection numbers, that's not required. Anyway, for now, that's an assumption. So for example, for SU2 0, we want the F2 realization, not the F0. Okay, so let's consider the 5-dimensional boundary. So this is the link of this canonical singularity. And there's a flavor symmetry. So like in this SU2 0 case, there was a non-compact divisor, and that gives rise to some local singularity that we can intersect with the boundary. So this S0 is a singularity that basically corresponds to the flavor symmetry being realized on the boundary. So from this boundary perspective, we know the one-form symmetry has this way of, we can think of it as, it comes from these non-compact 2 cycles that end on the boundary. So they're like 1 cycles. So these are these gamma 1, gamma I. And then 2 of these 1 cycles will basically be sort of related by this equivalence relation twiddle, so the associated line operators will be equivalent, if there is a chain C12 whose boundary is gamma 1, gamma 2. Right, so that's basically this field theory relation. L1 is equivalent to L2 by this local operator, now written in terms of the geometry. There's a 1 cycle here, another 1 cycle here, and if there's this yellow 2 chain that connects these and the boundary of these is that, then there's a local operator. I can wrap an M2 brain on this yellow thing, gives rise to local operator, and that's so puts the relation between L1 and L2 into this geometric context. So now we would like to take this picture and ask, can we see now the flavor symmetry? And you can see sort of here, so this part of this picture here will actually model the singularity. And now, so asking for this second equivalence relation, where we also have flavor symmetry considerations, just means now we excise part of this boundary, and then this equivalence relation will not actually hold anymore necessarily, because we excise this part here, and then in fact gamma 1, gamma 2 may not be equivalent because there's actually a third boundary from the flavor symmetry excision. So this twiddle relation basically does not include line changing operators that are charged under this center, so this thing that we quotiented from the flavor symmetry. So if we actually excise that from the link, then in fact 2 of these gammas may not be equivalent because you're actually getting here sort of, you excise this additional boundary. And in fact, if we now sort of run through this argument further, there's in fact this relation that this extension group E is given simply by the first homology of the link with this singularity excised. I think Jonathan will talk about this a bit more. So we can now put this further together, and there'll be some extension. This is sort of the extension sequence. This is E. This is the one-form symmetry. This is the center flavor symmetry. And there's now sort of a topological relation, which is precisely this extension group. Because we're actually running a little bit out of time, so I actually want to sort of get to some examples, and then I want to finish off with some more general thoughts. So what we actually have to do is compute all these groups, in particular H1 of the link minus this singularity. And to do that, we can use this nice result from Iñaki and Ben Heidenreich, who actually showed that the homology groups of these links in toric Calabi-Yau can actually be computed using collections, chains of length spaces glued together, where these length spaces are characterized as usually by some integers, and these are computed just very combinatorially from the toric diagram. So in particular, the one-form symmetry is going to be just H1 of this collection of length spaces, and is given in terms of the GCD of these Ni. And these Ni's are simply given in terms of the combinatorial data of the toric Calabi-Yau. So for example, if you have the vertices, then we can construct triangles of consecutive vertices, and then in fact these Ni's are just the areas related to the area of these triangles. And then to excise it, we just remove some of these vertices. That's sort of the idea. So in fact, there's sort of an associated collection of length spaces where we excise the singularity, and that gives us E. Okay, so let's look at the example we looked at before. So we have SU2, 0. This is again the toric diagram. So the one-form symmetry we get from this association of these length spaces. So we look at these triangles. So for example, here, this triangle here, this is area 2. So this is 2 times 1. So this is n is 2. The same happens here. And here the triangle is this vertex, this, and this vertex. And so in fact, in this case, you get a Z4. And the GCD of all these length space in I's is just going to be Z2, which is the correct one-form symmetry. Now to actually get the 2 group, we have to excise now the flavor symmetry node. So in fact, we remove this. And then these 2 length spaces actually become completely contractible. And so what we actually left with is just an S3 mod Z4 after we excise this sort of flavor symmetry vertex. And so in fact, this H1 of the link minus singularity is Z4. And that again is sort of exactly this extension that Z4 projects onto Z2, and then the center of the flavor is this Z2. And we can apply this now to many other examples. For example, SU2 and level 2n has one-form symmetry given by this. The flavor is again SO3. And then we have these toric diagrams. You can calculate the various length spaces, excise, compare, and get these kinds of extension sequences. And so we can see that there are now 2 groups precisely for this type class of models. I'm finishing off soon. It works for non-Lagrangian theories as well. That's not surprising. And let me now go to some comments. So I talked about this in the context of Calabi-Yau threefolds. In 5D, it can also be equally applied to G2, to F-theory models, to orbifolds, you name it. And all these constructions of higher form symmetries, higher group symmetries work equally well, and I think we'll hear talks about that later this week. One point that I think is sort of something that emerges thinking about these generalized symmetries even more and more is that a lot of the information is encoded in the boundary of the space. So in fact, not only the symmetries, so we've seen the one-form symmetry, 2 group symmetries are encoded in the boundary. In fact, we can also compute the anomalies for all these symmetries. So the Toft anomalies from something that we dubbed the SymTFT that goes back to Fried and appeared in this paper at the end of last year. So essentially that's, if you have a d-dimensional quantum field theory that you geometric engineer, you can construct this d+1 dimensional SymTFT, and that'll contain essentially the anomaly theory of your QFT. And that's derived essentially from first principles in supergravity, and I think Federico will talk about this later this week. And so that sort of speaks for the fact that a lot of this information is really encoded in the boundary of the compactification space. For example, you can compute anomalies for the 5D theories and find that there are, for example, anomalies of the one-form symmetry and mixed 0-1 anomalies. Okay, let me go to the outlook because I have 2 minutes left. So I think this program of determining all the symmetries, all the anomalies from the boundary of compactification or geometric engineering spaces is something that looks really sort of appealing, and also it puts a little bit of life to all these supergravity couplings that you'll actually see in many of the gauge supergravity literature. There are many couplings that actually come to life by interpreting them as background fields for certain fields as background fields for higher form symmetries, and the couplings as anomaly couplings for these QFTs. That's equally applicable both in geometric engineering as well as in holography. One thing that I didn't discuss much is what actually is the physics of these generalized symmetries. So in 4 dimensions, of course, one-form symmetries have a clear physical imprint in terms of confinement. Are interesting sort of associated physics interpretations of not just higher form symmetries, but also higher group symmetries, in particular in these higher dimensional theories. There's also, of course, a point that I didn't address at all, is all of this happened in geometric engineering. What happens as we couple gravity back? So how does this all tie in with the global symmetry conjectures? And finally, I think one point that is sort of in the making is how to actually realize non-invertible symmetries in these string theory compactifications, how to get sort of non-group-like symmetries in string theory. There are some ideas, but I think that's something we'll have to develop. So before I finish, and there are lots of activities on generalized symmetries this summer. There's an Aspen workshop, and there's also Simon's Center workshop on generalized symmetries in QFT and geometry. The application for that one is still open. So please, if you're interested to think about these things, you should go there. Okay, thanks for your attention. Questions? Yes, Gumon? Yeah. I don't believe so, but I think, Jonathan, you might talk about these orbifolds. Yeah, I don't think that in right. So how do the topological operators become non-invertible?
Any non-abelian orbifold in string theory will lead you to non-invertible symmetry.
Yes.
That's just by the selection.
Sure.
Of the two systems.
Yes.
So if you take the M theory in one higher dimension, you get one form version. You compactify them
Yes.
and you get the string version. So therefore, in 5D M theory, any non-abelian orbifold will automatically give you non-invertible double symmetries, one form double symmetry.
Cool. Interesting. Yes. Yes. Do you know how the actual topological how to see this from the topological operators, like how to construct the the flux operator and see the fusion?
For example, I think the example you mentioned was P2.
Yep. Yep. Yep.
And then you get Z3 one form symmetry that you mentioned.
That's right. There's a Z3 one form symmetry.
Z3 is the same Z3 what you used to call quantum symmetries of the
Yep.
orbifold. That maps to that same symmetry. So the non-abelian version of it is the non-invertible.
Cool. Okay. Very interesting. I will ask you more. Yes, Miriam. Yes. So you can also look at LPQRs. In fact, Dowie, why is he? I don't know why why my student, he's there. He's been looking at the related, also actually with fourfolds. You can look at YPQ over C2 and the whole lot. There actually the more subtle thing is, what is the physics associated? Can you actually learn something interesting in those cases? But yeah, all of this will apply equally in these. So the two groups, the one-form symmetries from the intersection numbers, which in that case I think you can also calculate H1 of the boundary and so on. All that is very well established computational, I think. It's a little bit more subtle to see from this boundary perspective. So I actually don't know in this LPQR whether there's some subtlety there. Yep, Aaron. Sure. Yep. That's right. So they'll be all gone by the time you couple it back. Yep. Absolutely. Yes, so here it seems to... That's right. That's right. So here, right, I was careful in saying, for example, the one-form symmetry here is not equal always to H1. There could be some subtleties in terms of that there are one cycles in the bulk. For the Calabi-Yau, this doesn't happen, but indeed it's coming from the boundary of these spaces. So when you actually have these boundaries are sort of you remove the bound, you close it, make it a compact model, these objects will disappear. So that's true, yes. Yeah.
Okay, very good.
Okay, thank you very much.
Thanks a lot, Sakura. And